Welcome! In today's video, I'm going to be going over the concepts behind Base64 encoding. I'll be going over a little bit about what it is, and then I'll show you how it works. So with that, let's get right into it. To start, let's talk a little bit about Base64's background. Base64 is what's referred to as a binary to text encoding, and as the name suggests, it was designed to allow unprintable binary data to be converted into printable ASCII characters without losing any information. It was originally designed for the MIME protocol, which was one of the protocols we use to send emails over a network. Emails are often sent out as text over networks like HTTP, and problems arise when binary attachments are included with the email, such as image files. To solve this, before the email is sent out, the binary data is first encoded into printable ASCII characters using Base64, and then sent out to a receiver. Once the message is received on the other side, the data is then decoded back into binary using Base64. In the modern world, Base64 has moved beyond simple email protocols, and we can now find them in many applications, including encoding file names, embedding images in web page documents, and even encoding certificates and keys in cryptography. So now that we know what it is, let's take a look at how it works. To encode binary information into printable text, we can break the process down into 4 simple steps. In the first step, we need to generate a Base64 table, which acts as a map between binary values and their Base64 ASCII character equivalents. The next step is to convert the data into 8-bit binary, if it isn't already, and combine all of the binary digits into one long binary string. We then take this string of binary digits and split it up again, but this time we do it into several 6-bit numbers. In the final step of encoding, the 6-bit numbers are used as a lookup into the Base64 table and matched with an encoded ASCII character. This character is appended to an output string, and we repeat this step until all 6-bit numbers have been converted into a character and added to the output string. This is all fairly straightforward, but it does warrant a closer look, so let's see these steps in action. In the first step, we talked about generating a Base64 table, and as the name suggests, the table has 64 entries in it. Before the table can be created, however, we first need to decide which set of 64 printable ASCII characters we want to use for the encoding. You should know, there are different implementations of Base64 which all use the same encoding method, but not every implementation uses the same character set. I won't get into all the differences between these character sets, but there is one set of characters that's most frequently used. This set starts by including all 26 capital letters, followed by all 26 lowercase letters, followed by all 10 numerical characters until we have 2 characters left. Here, the most common choice to use is a plus sign and a forward slash to round out all 64 characters. And again, not every implementation uses this character set, but this is the one that's most frequently used. So now that we have our character set, the next step is to simply build the Base64 table. We start by creating a table with 64 rows, numbered from 0 to 63. We then convert each of these numbers into a 6-bit binary value, and the reason for this will become apparent in a few moments. Finally, we finish the table by adding the letters taken from our character set, and we now have a table we can use to map the binary data. With the Base64 table built, the next step is to convert the data into binary. For this example, we can encode a simple text message like the one shown here. The encoding process is always done 3 bytes at a time. Once we've finished encoding the first 3 bytes of data, we grab the next 3 bytes and continue doing this until we reach the end. We'll talk later about what happens when there aren't enough bytes left to make a group of 3. For now, let's begin by taking the first 3 letters of the message. Since the data here is text, we'll first need to convert it into their binary equivalents. Of course, if the data is already binary, then this part is unnecessary, but the important thing to note here is that each byte of data must contain 8 bits. Some implementations of ASCII use 7 bits to represent characters, and in those cases, you'll need to make sure to pad the binary data with leading zeros. Either way, once we have the binary data, the next step is to combine the numbers together into one long string of 1s and 0s. We then split this string up again, but this time we split it into 4 6-bit numbers. This means if 3 8-bit numbers gives us a string of 24 digits in length, splitting the string into 6-bit numbers will give us 4 sextets for every 3 octets of data. And finally, with these 4 6-bit numbers, we can then pull up our Base64 table and look up each value for their corresponding ASCII character. For example, when we look up the first number in the table, we find its number corresponds to the number 16, which maps to the capital letter Q. The next number corresponds to the number 54, which maps to the printable character 2. This process continues for the other two numbers until we have all 4 encoded characters. And just like that, we now have the Base64 encoding for the letters capital C, A, N. But as I mentioned before, we operate with 3 bytes of data at a time. If we continue this encoding process for the remaining letters in the message, we end up with a string of characters that looks like this. Again, as you can see, for every 3 bytes of data, we convert those into 4 bytes of encoded data. But what happens if the number of bytes in the original message doesn't align exactly with a multiple of 3? If we take a look at the last cell of the table, we can see that there's only 1 character, but we still have 4 bytes of encoded text. What's more, the last 2 characters are equal signs, which don't even appear in the Base64 table. So what's going on here? Well, the answer is, when the data being encoded doesn't perfectly align with 3 bytes, we have the option to fill out the remaining portion with a special padding character. Depending on the implementation, this padding can either be mandatory, optional, or in some cases not even used at all. If you are using padding, then you only have the options of ending an encoded string with either 0, 1, or 2 padding characters. Most implementations use the equal sign for padding, but again, this doesn't always have to be the case. To fully understand padding, we can take a look at this in action using a quick demonstration. The first scenario happens when we only have 1 byte of data left to be encoded. In this case, we perform the same steps as before by first converting the data into their 8-bit binary equivalent. Next, we split the binary data into 6-bit numbers. But as you may have noticed, we don't have enough binary digits left to fill out the second 6-bit number. In this case, we simply pad the remaining digits with zeros, and we now have 2 6-bit numbers which can be used to look up the encoded characters in the Base64 table. Finally, since the last 2 6-bit numbers are empty, we add 2 extra padding characters to complete the encoded string. And we can see this once again, this time with 2 bytes of data. The same process is used as before, except this time there's only 1 single padding character added to the end. So that's it for the encoding. The decoding process is similar, except everything is done in reverse. I won't show a demonstration, but you can imagine starting with a string of encoded text, converting it into 6-bit numbers with the lookup table, combining the 6-bit numbers into a long string, and then breaking this binary string into 8-bit bytes of data. Of course, if the original data was text, then you would convert this binary data back into ASCII characters. So before I finish off this video, I do want to mention one of the drawbacks to using Base64. It's not a big one, but you should at least be aware of it. As we saw earlier, when we encode our data, for every 3 bytes of data that we have, we convert those bytes into 4 bytes of encoded text. This in effect increases the size of our data by a factor of 1/3. This of course is still a better choice than converting the data into hexadecimal, which would in effect double the amount of encoded data. But as I mentioned, you should at least be aware of the increase in the data size depending on how you plan on using it. Aside from this, and the fact that several different implementations of Base64 use different character sets, there really aren't that many other disadvantages to using it, which is why you can find it being used so frequently. And that's all for now. In this video, I introduced Base64 encoding, what it is, and how it converts data into printable ASCII characters. I hope you enjoyed this video, and I hope to see you the next time.